This is not a typical El Nino year. NOAA confirmed that on June 11, 2026, and what they confirmed is already doing something to America that most of the coverage has not described. The cattle auctions in Wyoming are running at 9 times their normal volume. The winter wheat harvest across the southern plains came up $1 billion short. The eastern edge of the Pacific Ocean has already crossed the threshold that defines a super El Nino, and it crossed that threshold before summer officially began. These are not forecasts. They are measurements that exist right now in federal databases, in livestock markets, in grain reports, and in a single number buried inside NOAA's June 11 report that did not appear in any headline published that morning. That number is the difference between understanding this as a weather story and understanding it as something that has already started reshaping the next 6 months of American life. The terrifying part is not what is coming. The terrifying part is what is already here. Stay with me, because the number we arrive at in the final part of this investigation will tell you exactly what the next 6 months of American weather are already set up to deliver, and you will not find that number in any headline published on June 11. If this has you concerned, subscribe to Rupture, because this channel reads the full report, not the headline pulled from page 1. Drop a comment below. What is the last time a weather forecast you watched on television actually told you what was already measured in the ocean 6 months before it arrived at your door? On the morning of June 11, 2026, a document was published at a government website that most Americans will never read, and the sentence at the top of it read as follows: El Nino conditions are present and expected to strengthen into the Northern Hemisphere winter 2026 to 2027. That sentence is not a forecast. That sentence is a declaration. It is the moment NOAA's Climate Prediction Center moved the status of the Pacific Ocean from a watch to an advisory, and the difference between those two words is not a technicality. It is the difference between a meteorologist saying conditions are favorable for something to develop, and a meteorologist saying the thing has now developed and you are inside it. Let me walk you through what that shift means in plain terms. An ENSO watch is the equivalent of a smoke detector beginning to chirp because the air in the room is changing. It is a notice that the system is monitoring an emerging condition. An ENSO advisory is the equivalent of the smoke detector telling you the fire is in the building. The Climate Prediction Center does not move from watch to advisory casually. The transition requires that observations, not models, have crossed specific thresholds in the Pacific Ocean and in the atmosphere directly above it. On June 11, those thresholds were crossed. The smoke detector stopped chirping. The alarm sounded. The document itself runs to several pages of dense oceanographic language, and most Americans who try to read it will give up after the first paragraph. That is not a failure of the reader. That is a feature of the document. It was written for the operational meteorology community, not for the family watching the evening news. But the language inside it, if you slow down and read it carefully, says something the headlines did not capture. The report states that sea surface temperatures in the central and eastern equatorial Pacific have warmed to the point of meeting the diagnostic criteria for El Nino. It states that anomalously high oceanic heat content, which is to say a much larger pool of warm water than is normal, has accumulated beneath the surface. It states that expanding westerly wind anomalies, which is to say wind patterns moving in the opposite direction from the normal trade winds, are now being observed across a wider stretch of the equatorial Pacific. Each of those phrases is a signal. Together they form a pattern. That pattern is what triggered the advisory. Not a single number, not a single image from a satellite. A convergence of measurements across the ocean, beneath the ocean, and in the atmosphere above it, all pointing the same way at the same time. The Climate Prediction Center does not issue an advisory because one buoy reads warmer than normal. It issues an advisory because the entire system has begun to behave consistently with an El Nino that is no longer forming. It has formed. Now, the numbers that mainstream coverage focused on are the ones that govern official classification. The Nino 3.4 index which is the standard measurement zone NOAA uses for headline classification, registered plus 0.7 degrees Celsius on June 11. The Nino 4 index, located further west, also registered plus 0.7 degrees Celsius. Those are the numbers you have heard. Those are the numbers that appeared in the wire services and the morning shows. Plus 0.7 in the Central Pacific. Plus 0.7 in the Western Pacific. Both readings above the half-degree threshold that defines a developing El Niño. Both readings consistent with what the advisory says is happening. But here is the question that the rest of this investigation will answer. If those are the numbers that justified the advisory, why does the rest of the June 11 document read like something much larger is already underway? The language inside the report is not the language of a borderline event. It is the language of an event that has already begun to organize itself with momentum. The phrases anomalously high oceanic heat content and expanding westerly wind anomalies are not descriptions of a system that is barely above the threshold. They are descriptions of a system that has built up reserves and is now beginning to use them. They are descriptions of a system with energy stored beneath the surface, waiting for the moment to release. The physical image that makes this concrete is one you can picture in your kitchen. Imagine a freezer that has been running on its lowest setting for years. The thermostat reads a temperature only slightly below the normal range, but inside the freezer. The contents are colder than they should be, the coils are working harder than usual, and the seal around the door has begun to release small puffs of cold air every time someone walks past. The thermostat reading does not tell you the full story. The full story is the accumulated state of the system. That is what NOAA's June 11 language describes. The thermostat reading, the plus 0.7, is real, but the accumulated state of the system, the heat content beneath the surface and the wind patterns above it, is what makes the advisory matter. The advisory itself was issued during what NOAA calls its monthly ENSO diagnostics discussion. This is a regular review cycle. Every month the agency's scientists gather to assess the state of the Pacific, look at the latest observations, run them against the model ensembles, and decide what category the system is currently in. Most months the answer is straightforward. The system is neutral, or developing, or persisting, or weakening. Once or twice in a generation the answer is different. June 11th, 2026 was one of those moments. The shift from watch to advisory in a single reporting cycle is not common. It does not happen because one variable nudged across a line. It happens because the entire convergence of variables has crossed at once. For older Americans watching this, the reference point that matters is this. The last time the Climate Prediction Center moved from watch to advisory at this stage of the calendar year, with this combination of ocean and atmosphere readings, the event that followed was one of the most consequential weather years in modern American history. That event has a name. We will get to it. For now, the point is this. The document published on June 11 is not a routine update. It is the official statement that the Pacific Ocean has crossed a line, and the United States is now downstream of whatever happens next. The headlines captured the declaration. They captured the 63% probability of a strong event by winter. They captured the plus 0.7 readings in the Central Pacific. What they did not capture is the rest of the document. They did not capture the language describing the heat content beneath the surface. They did not capture the description of the wind anomalies expanding eastward. And they did not capture the number that, in any other context, would have been the lead of every story written that day. That number is in the same document. It was published on the same morning. It was available to every reporter who downloaded the PDF. It just was not the number anyone chose to quote. That number is where we are going next. Let me introduce you to 3 stretches of open ocean in the equatorial Pacific that have no permanent human inhabitants, no ports, no buildings and no landmarks, and that are nonetheless among the most consequential pieces of geography on the surface of the Earth for anyone living in the United States. These are the 3 monitoring zones NOAA uses to read the state of the El Niño Southern Oscillation, which is the formal name for the ocean and atmosphere system that produces El Niño and La Niña. ENSO, in other words, is the engine. The three zones are the gauges on the dashboard of that engine. The first zone sits in the western equatorial Pacific, roughly between the dateline and the longitude that runs through eastern Indonesia. NOAA calls this region the Nino 4 zone, and it is the gauge that tells you whether the western Pacific, where the warmest water in the world ocean normally accumulates, is holding its heat or losing it. On June 11, 2026, the Nino 4 zone read plus 0.7 degrees Celsius above the long-term average. That is to say, the water in the western Pacific was about 3/4 of a degree warmer than it has been on average over the past several decades. 3/4 of a degree may not sound like much. In an ocean basin the size of the western Pacific, it represents an immense amount of stored energy. It represents a system holding heat above its normal capacity. Move east from the Nino 4 zone and you arrive at the second monitoring region. This one sits in the central equatorial Pacific, straddling the international dateline and extending eastward toward the longitude of Hawaii. NOAA calls this zone Nino 3.4, and it is the gauge that the agency uses for official classification of El Niño events. The thresholds are simple. A reading of +0, 5 degrees Celsius or higher in this zone, sustained over multiple months, is the criterion for a weak El Niño. +1.0 marks the threshold for moderate. +1.5 marks strong. +2.0 and above marks very strong, the category that gets called a super El Niño in the language used by climatologists and the press. On June 11, the Nino 3.4 reading was +0.7 degrees Celsius. That is above the weak threshold. It is the number that triggered the official advisory. It is the number that appeared in every headline. Now move further east, all the way to the eastern edge of the equatorial Pacific, to the stretch of ocean that runs along the coast of Peru and Ecuador. This is the third monitoring zone. NOAA calls it Nino 1+2, and it is the zone closest to South America, where the cold water of the Humboldt Current normally pushes up from the south and the upwelling of deep water normally keeps the surface cool. This is the zone where El Niño was first identified by Peruvian fishermen more than 100 years ago, who noticed that every few years, around Christmas. The cold water along their coast was replaced by warm water, and the fish disappeared. They named the phenomenon El Niño, which is Spanish for the boy child, because it arrived around the time of the Christmas holiday. The name stuck. The zone where the phenomenon was first recognized still bears its number. On June 11, 2026, the Nino 1+2 zone read +2, 1 degrees Celsius above the long-term average. Let me say that again, because the number does not register the first time you hear it. +2.1 degrees Celsius. 2.1 degrees above normal. In the monitoring zone closest to the South American coast, on the 11th of June, 4 to 6 months before the event is forecast to peak. Now +2.1 degrees Celsius is not a small anomaly. It is the value NOAA uses to classify a very strong El Niño at its peak in the Central Pacific. The very strong threshold for Nino 3.4 is +2.0 degrees Celsius. The reading in Nino 1+2 is already above that threshold. It is already at the level that, in the Central Pacific, would be the defining number of a super event. And it is at that level in June, not November, not December. It is at that level before the seasonal cycle that normally builds El Niño has fully begun. That is not weather. That is a system telling you something has shifted at the source. The reason the Nino 1+2 zone matters is that it is the leading edge. The eastern equatorial Pacific is where the warmth that disrupts American weather enters the system. When the upwelling along the Peruvian coast weakens, when the cold water from the Humboldt Current stops pushing north, the surface of the ocean off South America warms first. That warming then propagates westward along the equator, building up the heat content across the central and western Pacific and feeding the atmospheric mechanism that ultimately shifts the jet stream over North America. The eastern zone is not the official classification zone, but it is the early warning gauge. It is the place where the signal arrives before the rest of the system has caught up. Let me give you a household scale comparison. Imagine a long hallway with a furnace at one end and 3 thermometers placed along the floor, one at the far end of the hallway near the furnace, one in the middle and one near the front door. When the furnace kicks on, the thermometer near the furnace registers the change first. The middle thermometer responds next. The thermometer near the front door takes the longest to register. If you look at the front door thermometer alone, the hallway looks only slightly warm. If you look at the thermometer near the furnace, you can see that the system is running much hotter than the front door reading suggests. The Nino 1+2 zone is the thermometer near the furnace. The Nino 3.4 zone is the thermometer in the middle. The plus Nero 7 reading in the Central Pacific is the front door thermometer. It is real, but it is not the full picture of the system. Here is what makes the June 11 reading significant when you look at all 3 together. The Western Pacific, the Nino 4 zone, is holding plus 0.7. The Central Pacific, the Nino 3.4 zone, is also at plus 0.7. The Eastern Pacific, the Nino 1+2 zone, is at plus 2.1. The gradient is not flat, the gradient is steep. The eastern edge of the basin is running 3 times hotter than the rest. That is not the signature of a system in equilibrium. That is the signature of a system that has already begun to shift its mass of heat from one configuration to another, and the leading edge of that shift has already arrived. In the language of physical oceanography, this gradient is the early stage signature of a Pacific basin that is reorganizing itself. The warm water that normally sits piled up against the Western Pacific, held there by the trade winds blowing from east to west, has begun to slosh eastward. The trade winds have weakened. The pile has begun to redistribute. The leading edge of that redistribution shows up first in the eastern monitoring zone, because the eastern zone is at the receiving end of the slosh. By the time the central and western zones catch up, the eastern zone will already be at peak. That is what the June 11 numbers show. So here is the question that the rest of this investigation has to answer. How can the Eastern Pacific be at peak event levels 4 to 6 months before the event is forecast to peak? What is the mechanism that produces this kind of early stage signature? And if the leading edge has already crossed the super event threshold, what does that tell us about where the rest of the Pacific is heading? There is a name for the mechanism. There is a date attached to its discovery, and the NOAA report published on June 11 contains the exact language that confirms the mechanism is already active. The mechanism is what we look at next. Remember where we left it. The Eastern Pacific, the monitoring zone closest to South America, was reading plus 2.1 degrees Celsius on June 11, and that is the value NOAA uses to classify a very strong El Nino at peak, and this is June, not November. That is the gap. That is the number that did not appear in any mainstream headline on the day the advisory was issued. Let me show you why that number was not the lead of any story published on June 11. The reason is not malice. It is not censorship. It is the way agency communication works and the way news organizations have learned to translate it. NOAA's official classification of El Nino is based on the Nino 3.4 index. That is the standard. That is the number the agency uses to declare watches, advisories, and final event categories. Every wire service in the country, every meteorology desk at every television station, every climate reporter at every newspaper has learned over decades that when NOAA issues an ENSO update, the number to pull is the Nino 3.4 value. The headline writes itself, NOAA declares El Nino, Nino 3. 4 reads plus 0.7, 63% probability of a strong event by winter. That headline is accurate. That headline is responsible. That headline reflects the value the agency itself uses for official classification. So the question is not whether the headlines were wrong. The question is what they left on the page. What they left on the page is the Nino 1+2 reading. Plus 2.1 degrees Celsius, the eastern monitoring zone, the leading edge of the basin. the gauge that does not factor into official classification, but that tells you the trajectory of the entire system. Not a single mainstream outlet in the United States named that number in a headline on June 11. Not a single morning show pulled the Eastern Zone reading out of the report. The reporters who wrote those stories were not negligent. They were following the convention that has governed El Nino coverage for 40 years. They pulled the classification number and moved on. That is not the number you need to understand. The number you need to understand is the one they did not read aloud. Here is why the 1+2 reading matters independent of classification. The Nino 3.4 index was chosen as the official classification zone in the 1990s because it sits in the part of the Pacific where the atmospheric coupling, which is to say the connection between the ocean surface and the air above it, is strongest for predicting global weather impacts. That choice was sound. The Nino 3.4 reading is a good predictor of how El Nino will manifest in global circulation patterns, but the choice of Nino 3.4 as the official zone does not mean the other zones are irrelevant. They are not. Each zone tells you something different about the state of the basin. Nino 4 tells you what is happening in the warm pool at the western edge. Nino 3.4 tells you the central state, the one most useful for atmospheric coupling. Nino 1+2 tells you the leading edge, the part of the basin that warms first when the trade winds weaken, the part that is closest to the upwelling system off the coast of Peru. When the leading edge crosses the super event threshold in June, while the central zone is still at the weak threshold, you are looking at a basin that is loading its energy unevenly, with the eastern side ahead of the schedule that the central zone would predict. That uneven loading is not a curiosity. It is a forecasting signal in its own right. It tells you that the system is not following the gentle ramp-up pattern of a moderate event. It is following the steeper ramp-up pattern of a major event in its early stages. Let me give you the historical comparison that matters. In the spring and early summer of 1997, the same kind of early eastern warming was observed in the Nino 1+2 zone before the broader event classified as super. The eastern Pacific warmed early and aggressively that year. By June 1997, the Nino 1+2 zone was running well above the central Pacific reading. The central Pacific then caught up over the following months. By November 1997, the entire basin was in super event territory. The event peaked in late 1997 and into early 1998 with a Nino 3.4 reading of plus 2.4 degrees Celsius, one of the highest values in the modern record. The early leading edge signal in the spring of 1997 was not noise, it was the trajectory. The 2026 spring signal is structurally similar. The Nino 1+2 reading is already where the 1997 reading was when the Central Pacific had not yet caught up. The same uneven loading is visible. The same early warming at the eastern edge is observable. The same trade wind weakening is documented in the June 11 report. This does not guarantee that 2026 will follow the 1997 path. It does mean that the structural ingredients are in place for the path to be followed. Now let me name the part of this that requires some honesty. Climate scientists have been using a refined index in recent years called the Relative Oceanic Nino Index, or RONI, which is the standard Nino 3.4 measurement adjusted for the warming baseline of the surrounding tropical oceans. ONI, the Oceanic Nino Index, which is a 3-month running average of Nino 3.4 anomalies, is the classification standard. RONI is the refinement that climate researchers use to compare events across decades, accounting for the fact that the entire tropical ocean has been warming over time. The RONI value for June 11, 2026, sits at +1.4 degrees Celsius, which already places this event in the strong category by the relative measure, even though the headline ONI value sits at +0.7. The RONI value is the number that climate researchers find most useful for comparing 2026 to historical events. It is also a number that did not appear in any mainstream headline on June 11. There are reasons for that. RONI is a newer index. It is not yet the standard for official classification. Most reporters covering ENSO are not familiar with it. Some agencies are still in the process of integrating it into their public-facing communications. The reasons for its absence from headlines are institutional, not conspiratorial. But the absence is real, and the result is that the public picture of the June 11 event is anchored to the plus 0.7 only reading, while the underlying state of the basin, as measured by the RONI and as measured by the Nino 1+2 leading edge, is already at strong or very strong levels. Here is a way to hold the difference. Imagine you walk into a kitchen and look at the oven thermometer on the counter. It reads 350 degrees Fahrenheit. That is the official reading, that is the number the recipe calls for. But the oven itself has a built-in thermometer behind the door, and that one reads 425 degrees. The two thermometers are measuring different things. The counter thermometer is the standard. The built-in is the actual interior of the oven. If you only look at the counter, you think you are baking at 350. If you look at the built-in, you know the inside of the oven is much hotter than the official reading suggests. Both numbers are real, both are useful. But the difference between them tells you the system is not where the standard reading says it is. That is the situation on June 11, 2026. The official reading is plus 0.7. The relative reading, adjusted for the warming baseline, is plus 1.4. The leading edge reading in the zone closest to South America is plus 2.1. Each of those numbers is in the same document. Each of those numbers was published on the same morning, only one of them appeared in the headlines. So the structural question the viewer now has to hold is this. If the eastern edge is already at peak event levels, and the relative index already places the basin in the strong category, what happens when the rest of the Pacific catches up to where the leading edge already is? What does the basin look like when the central zone reaches the level the eastern zone reached in June? What does the basin look like when the western pool, which is currently holding plus 0.7, begins to lose its heat eastward to feed the system that is already loading on the other side? The answer to that question requires understanding the mechanism that drives the entire process. The mechanism has a name. It was identified by a scientist whose work was published in 1966, and it is the reason the June 11 readings are not three independent numbers. They are three readings from the same engine. That engine is what we examine next. Let me ask you something that sounds like it belongs in a physics class, but that will matter to everyone watching this by the time we reach the end. Why does the ocean off the coast of Peru warm up before the central Pacific does? And why does that warming, once it begins, tend to keep going? The answer to that question is the difference between understanding El Niño as a forecast and understanding it as a process that has already begun and that is now reinforcing itself. The mechanism has a name. It is called the Bjerknes Feedback, and it was identified by Jacob Bjerknes, a Norwegian-American meteorologist, in a paper published in 1966. Bjerknes had spent decades studying the relationship between the Pacific Ocean and the atmosphere above it. He was the first scientist to articulate, in clear physical terms, the loop that connects the two. The loop is not a theory. It is the documented physical mechanism that governs every major El Niño event in the modern record, including the one declared on June 11, 2026. Let me describe the loop using an image you can picture in your kitchen. Imagine a long bathtub filled with water, sitting level on the floor. The water sits evenly across the length of the tub. Now imagine that a steady current of air is blowing across the surface of the water, from one end of the tub to the other, pushing the surface water in the direction of the wind. Over time, that wind piles the water up against the far end of the tub. The water level at the far end is now higher than the water level at the near end. The far end is also warmer because the wind has been pushing warm surface water in that direction for a long time. The near end, where the wind started, is colder because the water at the surface has been pushed away and replaced by cooler water rising up from below. That bathtub is the equatorial Pacific Ocean. The wind blowing across it is the trade winds, which normally blow from east to west across the equator. The far end of the tub, where the warm water piles up, is the Western Pacific, near Indonesia and the Philippines. The near end, where cooler water rises from below, is the Eastern Pacific, off the coast of Peru. That is the normal state of the system. That is what oceanographers call the Walker circulation, named after the British scientist Gilbert Walker, who first described the atmospheric component of it in the 1920s. The Walker circulation is the wind belt. The bathtub tilt is the ocean response. Now, what happens when the wind belt weakens? The water that was piled up against the far end of the tub begins to slosh back. It moves eastward. As it moves, it carries warm surface water with it. The eastern end of the tub, which was previously cooled by water rising up from below, begins to warm up because warm water is now arriving from the west. That warming is what shows up in the Nino 1+2 monitoring zone. Here is where the feedback begins. When the Eastern Pacific warms, it warms the air directly above it. Warm air rises. Rising air creates low pressure at the surface. Low pressure at the surface in the Eastern Pacific reduces the pressure difference between the eastern and western ends of the basin. The trade winds, which normally blow from east to west because of that pressure difference, weaken further. Weaker trade winds allow more warm water to slosh eastward. More warm water in the east warms more air above it. The air rises faster. The pressure drops further. The winds weaken more. The water sloshes faster. The east warms more. That is the loop. It feeds itself. Each step makes the next step more likely. The technical term is positive feedback, which is to say a system in which the output of each cycle becomes the input of the next, amplifying the signal rather than dampening it. This is not how most systems in nature behave. Most natural systems are governed by negative feedback, which is to say processes that dampen disturbances and return the system to equilibrium. The Bjerknes feedback is the opposite. Once it crosses a critical threshold, it accelerates toward its own conclusion. The June 11 NOAA report contains the exact language that confirms the Bjerknes feedback is already active in the Pacific right now. The report describes anomalously high oceanic heat content, which is the bathtub holding more warm water than normal. It describes expanding westerly wind anomalies, which is the trade wind belt weakening, and beginning to reverse over portions of the equatorial Pacific. Westerly means blowing from the west. The normal trade winds blow from the east. When the winds in a portion of the equatorial Pacific begin to blow from the opposite direction, the bathtub stops being held in place. The slosh accelerates. The feedback intensifies. Both signatures are documented in the report. The heat content signature is in the ocean. The wind anomaly signature is in the atmosphere. When both signatures are present at the same time, you are not looking at a system that is forming. You are looking at a system that is running. The June 11 language confirms that the Bjerknes feedback is not waiting to begin. It has begun. Let me give you a second household scale image to hold this. Imagine you are standing in a room where the thermostat is set to a comfortable temperature, but there is a heater under the table that is running on its own. The heater warms the air near the table. The warm air rises. As the warm air rises, it creates a small convection current. The convection current draws cool air from the corners of the room toward the table. The cool air arrives at the heater, gets warmed, rises, and the cycle continues. The room is not yet uncomfortably warm. The thermostat has not yet registered the change. But the convection current is running. The system has organized itself around the heater. By the time the thermostat reads the change, the air movement pattern in the room is already established. That is what is happening in the Pacific right now. The Bjerknes loop is the convection current. The June 11 readings are the early thermostat registration. The advisory is the agency confirming that the loop is running. The +2, 1 degrees Celsius in the Nino 1+2 zone, is the leading edge of that loop, where the warm water has already arrived. The +0.7 in the central zone is the middle of the room, where the air has begun to warm, but the convection pattern has not yet fully equalized. The critical phrase to hold is this one. The Bjerknes Feedback, once it crosses a critical threshold, becomes the dominant driver of the system. It runs toward its conclusion unless the trade winds reorganize around a new configuration or the oceanic heat content depletes faster than the loop can sustain. Neither of those exits happens in weeks. They happen over months. And in June 2026, neither exit is visible in the data. Neither of those two endpoints happens in weeks. They happen in months. The typical El Niño event runs for 9 to 12 months from the onset of the feedback to the peak of the redistribution. That is the consequence of self-reinforcement. The system does not respond to short-term variability. It responds to the cumulative state of the loop. A week of stronger trade winds in July will not stop the process. A week of weaker trade winds in August will not accelerate it dramatically. The loop is governed by the integrated state of the basin, not by week-to-week noise. That is why the June 11 readings matter so much more than they appear to matter at first glance. They are not a snapshot. They are a confirmation that the loop has crossed the threshold where it is sustained by its own internal mechanism. The trajectory from June 11 forward is not random. It is the working out of a process that has already started, that has already organized the Pacific Basin around itself, and that has already begun to manifest in the readings the agency published. What that loop produces in terms of probability and intensity is the next layer to examine. In the history of NOAA's El Niño forecasting, it is extremely rare for 13 separate international model ensembles to produce the same category prediction at the same time. The models are run by different agencies in different countries, using different assumptions, different initial conditions, and different mathematical structures. They are designed to be independent of one another, so that when they agree, the agreement carries weight, and when they disagree, the disagreement reveals which assumptions matter. On June 11, 2026, the Erie/Columbia University Super Ensemble, which aggregates all the major international models into a single probability summary, reported that all 13 contributing ensembles were pointing the same direction. Every one of them predicted at least strong category intensity for the 2026 to 2027 event. Every one of them. That is convergence. That is the kind of agreement that almost never happens in operational forecasting. A month earlier, the same super ensemble had reported an 82% probability of El Niño conditions persisting through the winter. On June 11, that number was 98%. The probability did not drift upward, it jumped. A 16-point increase in a single monthly cycle is not the signature of a system that is gradually moving toward a forecast. It is the signature of a system that has crossed a threshold the models can now resolve with much higher confidence. Let me walk you through what that increase means in plain terms. Climate models do not produce certainty. They produce probability distributions. A model run that says there is an 82% chance of an outcome is saying that across the range of plausible initial conditions the model can resolve, 82% of the simulated futures end with that outcome, and 18% end with something else. When the same model the following month says 98%, what has changed is the underlying state of the system the model is reading. The initial conditions have moved closer to a state where almost every plausible future leads to the same outcome. The dispersion of possible futures has narrowed. The forecast is no longer reading a range of possibilities. It is reading a state that funnels into one outcome. That is what self-reinforcing means in practice. A non-self-reinforcing system, when measured month to month, produces forecasts that wobble. The probability of an outcome goes up and down depending on short-term variability in the inputs. A self-reinforcing system produces forecasts that consolidate. The probability of an outcome rises steadily, with each month's reading pulling the forecast distribution tighter around a single trajectory. The jump from 82% to 98% in a single cycle is the consolidation signature. The North American Multi-Model Ensemble, which NOAA itself runs in cooperation with several research institutions, makes the specific prediction that the event will intensify through the winter of 2026 to 2027, peaking in the November to January window. That is the standard timing for a major El Nino. The peak is what determines the category. If the Nino 3.4 index crosses plus 1.5 degrees Celsius and holds, the event is classified strong. If it crosses plus 2.0 and holds, the event is classified very strong, which is the super event category that the 1997-98 and 2015-16 events reached. The North American Multi-Model Ensemble currently projects that the event will reach at least the strong category, with significant probability of crossing into the very strong category by peak. Here is the comparison that makes the probability concrete. Imagine you are sitting in your driveway watching a thunderstorm approach from the west. An hour ago you looked at the radar and the storm was 100 miles out, and the forecast said there was an 82% chance it would pass over your town. You went back to your day. A few minutes ago you checked again, and the radar shows the storm is now 60 miles out, and the forecast says there is a 98% chance it will pass over your town. What changed in that hour is not the storm. The storm has been doing the same thing the entire time. What changed is your distance from it. The storm has moved closer. The cone of uncertainty has shrunk. The probability has tightened around a single outcome because the system is now close enough to be resolved with high confidence. That is what the 98% figure represents. The Pacific Ocean is no longer 100 miles away. The storm has moved closer to the driveway. The models can now see the trajectory with the kind of resolution that produces near certainty. That is not hype. That is what the convergence of 13 independent ensembles at 98% agreement means. Now the question this raises is the one the viewer should hold for the rest of the investigation. If 13 models are pointing the same direction, and the probability of strong El Nino conditions persisting through the winter is at 98%, what does that actually mean for the winter that is now 6 months away? It means that the planning horizon for what the United States is going to experience in November, December, January and February is no longer in the realm of possibility. It is in the realm of preparation. The agencies that govern water management, agriculture, emergency response and energy distribution treat a 98% forecast differently than they treat a 60% forecast. The 60% forecast is a watch posture. The 98% forecast is an operational posture. The other dimension of self-reinforcement that matters here is what the loop does in the next several months. The Bjerknes Feedback we examined in the previous part is the engine. The model probabilities we are examining now are the gauge that reads the engine. Both are pointing the same direction. Both are accelerating in the same way. That is the meaning of self-reinforcement. The engine and the gauge are not independent observations. They are two views of the same process. When the engine runs harder, the gauge moves further into the high confidence zone. When the gauge moves into the high confidence zone, it confirms that the engine is sustained. The 13 models include the European Centre for Medium-Range Weather Forecasts, the United Kingdom Met Office, the Australian Bureau of Meteorology, the Japan Meteorological Agency, Environment and Climate Change Canada, and several research institution models from the United States and Europe. These are not models that share assumptions. They are not models that run on the same codebase. They are not models that are reading the same observations through the same lens. They are independent. Their agreement at 98% is the kind of result that statisticians describe as low probability under the null hypothesis of disagreement, which is to say that the probability that all 13 models would agree at this level if the underlying signal were weak is vanishingly small. The signal is not weak. The signal is the loop running, the basin reorganizing, and the gauge tightening around a single trajectory. The 98% number is the most honest representation of where the Pacific Ocean was on June 11, 2026, that a probability distribution can produce. It is not a guarantee. Nothing in operational forecasting ever is, but it is the highest confidence forecast for a major ENSO event that the international model community has produced in recent memory. That trajectory has been seen before, with documented consequences, in a year most Americans over the age of 55 will remember. 13 models pointing the same direction and a self-reinforcing mechanism already confirmed as active. That combination has happened before, and the record of what followed is not a forecast. It is the actual documented outcome of the last time the Pacific Ocean did what it is doing right now. The year was 1997. The event began with early warming in the eastern equatorial Pacific in the spring, very similar in structure to what is being observed in June 2026. The Nino 1+2 zone warmed first. The central Pacific caught up over the summer. By autumn, the entire basin was in super-event territory. The Bjerknes Feedback that drove the 1997 event was the same mechanism that is running in the basin today. The trade winds weakened in the spring. The warm water pile in the western Pacific began to slosh eastward. The eastern Pacific warmed. The atmosphere coupled to the warming ocean. The feedback loop accelerated. By November 1997, the Nino 3.4 reading had climbed to plus 2.0 degrees Celsius. By the peak in late 1997 and into early 1998, the reading reached plus 2.4 degrees Celsius, one of the highest values in the modern record. That peak was not an abstraction. It produced documented consequences for the United States that the federal government tracked, recorded and published. The National Climatic Data Center, which is now part of NOAA's National Centers for Environmental Information, compiled a record of the 1997-98 event in a series of post-event analyses. Those analyses are public. They are searchable. They contain the numbers that follow. 189 people did not survive the American weather that followed the 1997-98 El Nino. They did not survive the tornadoes it produced. They did not survive the floods it delivered. They did not survive the storms it steered over the southern tier of the United States, while the northern states ran warm and dry. The direct economic losses attributable to the event in the United States totaled approximately $4 billion in 1998 dollars, which adjusted for inflation is several times that figure today. Storms struck California from the Pacific with a persistence and intensity that the state had not seen in a generation. Tornadoes formed across the southeastern United States in the early months of 1998 in numbers that exceeded the long-term average. Flooding hit the Gulf Coast states repeatedly through the winter. The Pacific Northwest received above normal precipitation. The Northern Rockies and the Ohio Valley ran warmer and drier than normal, which contributed to a quiet but consequential drought signature in the agricultural heartland. This outcome was not random. It was the jet stream moving, which is what El Nino does when it reaches the level the 1997 event reached. The mechanism that produced all of it has a name. It is the Bjerknes Feedback, the same self-reinforcing loop that the June 11 NOAA report describes as active in the basin today. And that name, that exact mechanism, appears in NOAA's June 11 report as the operational explanation for what is being observed in the Pacific right now. Let me walk you through what made 1997 specifically lethal. The 189 deaths were not concentrated in a single event. They were distributed across the months of the El Nino winter, in different states from different proximate causes. They were the cumulative human toll of a weather pattern that had been reshaped by an ocean temperature anomaly thousands of miles away. A farmer caught in a tornado in Florida, a driver swept off a flooded road in Texas, a family in a mobile home that did not survive a storm in Alabama, a hiker in California who underestimated the persistence of a Pacific storm system. The deaths were not concentrated. They were geographic. They followed the path of the shifted jet stream. Let me give you the specific human geography of that winter. Central Florida had a tornado outbreak in February of 1998 that killed 42 people in a single night. The Kissimmee storm system produced multiple long-track tornadoes that moved through populated areas in the dark after sunset when warnings reach fewer people. The death toll from that single outbreak was the deadliest tornado event in Florida history. The outbreak was directly attributed by the National Weather Service to the El Niño-driven jet stream pattern that had brought enhanced moisture and instability to the Gulf of Mexico region throughout that winter. California received more than twice its normal seasonal precipitation in the winter of 1997-98. The persistent storm track that El Niño produces in the eastern Pacific delivered atmospheric river after atmospheric river to the California coast. Mudslides killed multiple residents in the Bay Area and in the foothills of the Sierra Nevada. The agricultural losses in the Central Valley were significant. Insurance claims from storm damage in California alone exceeded several $100 million. The Gulf Coast and the southeastern United States experienced repeated flooding events through the winter. Cities along the Gulf saw above normal rainfall in months that are normally dry. The Mississippi River system carried elevated flows for weeks at a time. The flooding contributed to crop losses, infrastructure damage, and several drowning deaths across the region. The northern tier of the country received a different signature. The Pacific Northwest had a wetter than normal winter, consistent with the storm track that El Niño produces in that region during major events. The northern Rockies and the Great Plains ran warmer than normal. The Ohio and Tennessee valleys ran drier than normal, with reduced winter precipitation that left soil moisture deficits going into the 1998 growing season. That is the signature. A southern tier hit by storms and water, a northern tier running warm and dry, a jet stream pulled south, delivering moisture and instability to one half of the country and steering it away from the other. Every weather event that produced the 189 deaths can be traced to that jet stream shift. The jet stream shift can be traced to the ocean and atmosphere coupling in the equatorial Pacific. The coupling can be traced to the Bjerknes Feedback. The feedback was first identified by Bjerknes in 1966. The mechanism appears in NOAA's own language in the June 11, 2026 report. The 1997-98 event was not a freak occurrence. It was the working out of a specific physical mechanism that the agency has been monitoring for decades. The 2026 event has the same early signature, the same eastern Pacific warming pattern, the same trade wind weakening, the same anomalously high oceanic heat content. The structural ingredients that produced the 189 deaths in 1997-98 are present in the basin right now. This part does not yet connect 1997 to 2026 explicitly. It does not yet say that the 2026 event will produce the same outcome. It cannot say that, because the trajectory is still unfolding. What this part says is that the structural mechanism is the same, the early signature is the same, the agency is using the same language, and the international model community is in agreement at 98% that the event will reach at least the strong category. Those are the facts. The viewer holds both events simultaneously now. The 1997 record on one side, the 2026 trajectory on the other. The connecting mechanism in the middle. What that mechanism does to American weather, specifically, is what we examine next. There is a river of air moving at speeds above 100 miles per hour at an altitude of 6 to 9 miles above the surface of the Earth, and it is the primary mechanism through which a temperature anomaly in the Pacific Ocean becomes a flood in Louisiana or a drought in Montana. That river is called the jet stream. It is the steering current for the storm systems that cross the continental United States from west to east. When the jet stream is in its normal position, the storms it carries take a normal track. When the jet stream shifts, the storms shift with it. The position of the jet stream in winter is one of the most consequential physical variables for American weather, and El Niño is one of the most powerful drivers of where the jet stream sits. Let me walk you through what the jet stream does in plain terms. The Earth's atmosphere is divided into layers. The layer closest to the surface, where weather happens, is called the troposphere. At the top of the troposphere, where the temperature stops dropping and starts to level off, there is a boundary called the tropopause. Just below the tropopause, at altitudes between 6 and 9 miles above sea level, there are bands of fast-moving air that circle the planet. These bands are the jet streams. There are several of them, in both hemispheres. The one that matters most for the United States is the polar jet stream, which separates cold polar air to its north from warmer mid-latitude air to its south. The polar jet stream is not a fixed band, it wobbles. It moves north and south depending on the temperature gradient between the polar region and the tropics. In winter, when the polar region is much colder than the tropics, the jet stream tends to be stronger and more compact. In summer, when the temperature gradient relaxes, the jet stream weakens and shifts northward. Within any given season, the jet stream also responds to large-scale forcing from the oceans below it. The Pacific Ocean is one of the largest forcings. When El Niño warms the central and eastern equatorial Pacific, it changes the temperature gradient that the jet stream responds to. The warm Pacific heats the air above it. The warm air rises. Rising air at the equator creates upper-level outflow that propagates northward and southward. That outflow reorganizes the position of the subtropical and polar jet streams over the Pacific basin. The subtropical jet, which sits south of the polar jet, strengthens and shifts northward. The polar jet, instead of taking its normal northern position over the Pacific Northwest and southern Canada, gets pushed south. By the time both jet streams have crossed the west coast of the United States, they are positioned further south than they would be in a non-El Niño winter. That southern shift is the mechanism that produces the documented impact geography of an El Niño winter. NOAA's Climate Prediction Center publishes seasonal impact maps that show the typical El Niño signature for the United States. The southern United States, from California across the Gulf Coast to Florida, faces wetter than normal winters. The reason is the storm track. The southern shifted jet stream steers Pacific storms across the southern tier of the country, delivering precipitation to regions that would normally be drier in winter. The Pacific Northwest, where the storm track normally delivers winter precipitation, often runs drier than normal because the storms have been pulled south. The northern Rockies, the Ohio and Tennessee valleys, and the upper Midwest tend to run warmer and drier. The Northeast can be variable, but often runs milder than average. The physical image that clarifies the jet stream is a simple one. Imagine a garden hose lying on a sloped driveway. The hose is the storm track. The water flowing through it is the moisture and energy that storms carry. When the hose is in its normal position, the water lands in one part of the driveway. When you pull the hose to one side, the water lands somewhere else. The hose has not changed. The water has not changed. The aim has changed. That is what the jet stream shift does to American weather. The same amount of total energy and moisture moves across the country, but it is aimed at different regions. The specific regional outcomes during major El Niño events are documented across decades of records. The southern United States, including the Gulf Coast, often experiences above normal winter precipitation, increased frequency of severe weather outbreaks in late winter and early spring, and elevated flood risk in lowland areas. The Florida Peninsula has historically seen increased tornado activity during major El Niño winters, a pattern that culminated in the 1998 Kissimmee outbreak. California sees more frequent and more intense atmospheric river events, which deliver large amounts of precipitation in short periods. The desert Southwest receives more winter rain than usual, which can be beneficial for drought-stricken regions, but also produces flash flood risk. The northern tier signature is the inverse. The Pacific Northwest often runs drier and warmer, which affects snowpack accumulation in the Cascades. The northern Rockies, including Montana, Wyoming, and Idaho, run warmer and drier through the winter, with reduced snowpack and elevated wildfire risk going into the following summer. The Ohio Valley and the Tennessee Valley experience lower than normal winter precipitation, which can stress water supplies and reduce soil moisture for the following growing season. The Great Lakes region and the Northeast can run milder than average, with reduced lake effect snowfall and lower heating demand. The agricultural implications of this geography are substantial, and they are not equal across regions. Winter wheat in Oklahoma and northern Texas can benefit when the storm track delivers moisture consistently through the growing months. A rancher in the Texas Panhandle is watching the same jet stream forecast that a meteorologist in College Park is reading, because both of them know that the difference between a wet winter and a dry one is the difference between a crop and a loss. But the same storm track that saves the southern wheat grower can drown the cornfields of a central Iowa farmer who gets too much rain at the wrong time, or leave a spring wheat grower in North Dakota with too little moisture at the only time it matters. Do not move past that regional split. Because the jet stream does not negotiate. It delivers its moisture where the physics put it, not where the need is highest. The energy sector carries the same asymmetry. Heating demand in the warmer southern states drops during El Niño winters. Utility companies in those states plan around that reduction, but the northern states, which also run milder, see their demand assumptions shift too, and the utilities that overordered fuel for a cold northern winter are now sitting on supply they cannot move. Now, the question that the structural data raises is this. What happens to the southern tier regions if this El Niño crosses into very strong territory, which is where the June 11 data says it is headed? The historical record suggests that very strong events produce amplified versions of the typical impact signature. The storm track is more persistent. The precipitation totals are higher. The severe weather outbreaks are more frequent. The 1997-98 event produced what was at the time the deadliest tornado outbreak in Florida history. The 1982-83 event, which was also very strong, produced widespread flooding across California and severe storm impacts across the Gulf Coast. The 2015-16 event was strong but had a different geographic emphasis, with significant impacts in California and the Pacific Northwest. The very strong category does not guarantee a specific regional outcome. It does indicate that the amplitude of the impacts tends to be larger than what a moderate event produces. The southern tier of the country, in particular, tends to bear the brunt of major El Niño winters, because the storm track shift is most pronounced over the regions closest to the equatorial Pacific. That impact geography is what the June 11 forecast trajectory is pointing toward. But the impact geography is not limited to the storm track over land. There is a coastal dimension to El Niño that operates through a different mechanism, and that mechanism is already producing measurable effects along both American coastlines. Let me walk you through something that NOAA published on May 15, 2026 that never made the evening news, and that is the most direct statement any agency has made about what this El Niño is already setting up for the American coastline. The publication came from NOAA's National Ocean Service, which is the branch of the agency responsible for monitoring coastal water levels, tides and storm surge. The report addressed the coming high tide flooding outlook for the 2026 to 2027 tide year, which runs from May through April. The report integrated two factors that the agency stated were converging in a way that has not been fully captured in mainstream coverage. The first factor is the steady long-term sea level rise that has been observed at tide gauges along the United States coastline for decades. This is the background condition. Sea level along most American coastlines is higher today than it was 20 years ago, higher than it was 40 years ago, higher than it was when most viewers were born. The rise has not been dramatic in any single year. It has been incremental. But the cumulative effect over decades has been to push the baseline water level closer to the elevations at which coastal flooding occurs. Streets that flooded only during major storms in the 1980s now flood during routine high tides. The second factor is El Niño. NOAA oceanographer William Sweet, in the May 15 report, described the convergence of these two factors as a double whammy. That is the word he used, double whammy. The decades of sea level rise have pushed the baseline up. El Niño, through its specific oceanographic mechanisms, is now adding additional water on top of that baseline. The result, in the agency's own published language, is the expectation of more frequent, deeper and more widespread high tide flooding along both the west and east coasts. The mechanism by which El Niño raises coastal sea levels is worth slowing down for. It operates through several physical processes. The first is the redistribution of water mass within the Pacific Basin, which we examined in the discussion of the Bjerknes Feedback. When the trade winds weaken and the western Pacific warm pools slosh eastward, the sea level at the eastern edge of the basin rises. That is not a metaphor. It is a measurable rise in the actual height of the ocean surface along the west coast of the Americas. The rise can be several inches during a strong El Nino, and several inches matters along a coast where the baseline is already close to flood thresholds. The second mechanism is Kelvin waves. Kelvin waves are not ocean waves in the surf sense. They are slow, deep planetary scale pulses of warm water that travel along the equator just below the ocean surface, from west to east, in response to wind anomalies in the western Pacific. When the trade winds weaken, Kelvin waves are generated. They cross the equatorial Pacific in a matter of weeks. When they reach the eastern boundary of the basin, they bend northward along the coast of the Americas and propagate up the coast as coastal Kelvin waves. These waves carry warm water with them. They raise sea levels along the coast. They reduce the upwelling of cold, deep water. The result is a warmer, higher ocean surface along the west coast of the United States during El Nino winters. The third mechanism is the change in storm track that we examined in the previous part. The southward shifted storm track over the Pacific delivers more storms to the west coast. Each storm brings its own surge, its own wave run-up, its own coastal flooding potential. When the baseline is already elevated by sea level rise and by the Kelvin wave contribution, each storm's additional contribution lands on top of a higher starting point. The flooding that results is deeper and more widespread than the same storm would produce in a non-El Nino year. The Atlantic and Gulf coasts experience a different signature, but a related one. El Nino's influence on the Atlantic basin operates partly through the upper-level winds that move from the Pacific eastward. The result is increased wind shear over the Atlantic during hurricane season, which tends to suppress Atlantic hurricane activity. That is a piece of conventional El Nino wisdom that has been documented for decades. But it is only part of the story. The Gulf and southeast coasts also experience above normal winter rainfall during El Nino because the southern shifted jet stream delivers storms across the Gulf and over the Florida Peninsula. The combination of elevated baseline sea levels from long-term rise, plus the additional precipitation from El Nino-steered storms, produces what the May 15 report describes as elevated tides and stronger surf on the west coast, storm surge on the Atlantic coast, and above normal rain on the Gulf and southeast coasts. The image that captures the coastal situation is this. Imagine a kitchen sink that has been slowly accumulating water from a tap that has not been fully turned off for years. The water level has risen close to the rim of the sink. Most days the level holds steady just below the overflow, but on a day when someone places a large bowl in the sink, displacing additional water, the level rises above the rim. The water spills onto the floor. The sink itself has not done anything new. The tap has been running at the same rate. What has changed is the cumulative state of the sink and the addition of the bowl. That is the coastal flooding situation along American shorelines in 2026. Decades of slow rise have brought the water level close to the rim. El Nino is the bowl placed in the sink. The combination is what produces the spillover. The specific implication for older Americans living in coastal communities is direct. The viewer who lives in a coastal community from the Pacific Northwest down to the southern tip of Florida is in a region that NOAA has named in its May 15 report. The report does not say that catastrophic flooding will occur in any specific neighborhood at any specific date. It says that high tide flooding events, which are the smaller, more routine flooding events that occur during king tides and during the higher tides associated with new and full moons, will be more frequent, deeper, and more widespread than in non-El Nino years. The events that did not flood a street in 2024 may flood it in 2026. The events that flooded one block in 2024 may flood 3 blocks in 2026. Coastal communities have been adapting to long-term sea level rise for years. Many cities have installed pumps, raised seawalls, elevated critical infrastructure, and revised their stormwater management. those adaptations were calibrated to the baseline rise. They were not calibrated to the additional contribution that are very strong El Niño layers on top of that baseline. The May 15 report is essentially the agency notifying coastal infrastructure managers that the calibration may need to be revised for the 2026 to 2027 tide year. The communities most directly named in the impact geography include the major West Coast cities from Seattle down through San Francisco, Los Angeles and San Diego, where Kelvin wave contributions and storm track effects converge. On the East Coast, the Mid-Atlantic region from Norfolk through the Delmarva Peninsula up to coastal New Jersey faces elevated storm surge risk if El Niño-steered systems track far enough north. The Gulf Coast, from Texas through the Florida Panhandle, faces above normal winter rainfall combined with elevated tide levels. The Florida Peninsula itself, including the Atlantic coast from Miami up through Jacksonville, faces the combination of above normal rainfall and elevated baseline sea levels. The most important framing the May 15 report provides is that the high tide flooding that occurs in El Niño years is not a single dramatic event. It is a chronic condition. It is many small flooding events occurring more often than usual, each one degrading infrastructure, each one disrupting daily life in coastal neighborhoods, each one accumulating into a winter of sustained nuisance and intermittent damage. The viewer who watches the evening news for a single catastrophic event may miss the chronic dimension entirely. The chronic dimension is what NOAA has now publicly forecast. That chronic dimension extends inland in a different form. The Drought Monitor has been running its own readings of the country, and what it shows is the inverse of the coastal flooding picture. While the coastlines are being recalibrated by rising sea levels and incoming storm tracks, something is happening inland that most El Niño coverage has not addressed, and the Drought Monitor published it in plain numbers on June 9. The US Drought Monitor is the joint federal product produced weekly by the National Drought Mitigation Center at the University of Nebraska in partnership with NOAA and the ISDA. It is the most authoritative single-source reading of drought conditions across the continental United States. The June 9, 2026 reading showed that 56.16% of the lower 48 states were in some level of drought. That is more than half the country. That is the baseline condition into which El Niño is now arriving. Let me walk you through what that 56% figure means in plain terms. The Drought Monitor uses 5 categories. The lightest is D0, abnormally dry, then D1, moderate drought, then D2, severe drought. D3 is extreme drought. D4 is exceptional drought, the most intense category, used only for the most severe and prolonged conditions. The 56.16% figure includes all categories from D1 through D4. Areas in D0 are not counted in that figure, even though they are drier than normal. The areas in D1 through D4 are areas where drought is being measured as a meaningful impact on vegetation, water supply, and agriculture. The June 9 reading also showed that severe drought, the D2 category, was expanding into regions that had not been in that category in recent months. The Northeast, the Mid-Atlantic, and Minnesota were among the regions where D2 was advancing. These are regions that by their climate norms are not typically associated with significant drought conditions. The Mid-Atlantic region has experienced below normal rainfall for several consecutive months in 2026. The Northeast, including parts of New England, has seen reduced summer rainfall and elevated evapotranspiration from a warm spring. Minnesota and the upper Midwest have seen reduced snowpack accumulation in the preceding winter and reduced spring rainfall. The Southern Plains drought has a longer history. According to data from drought.gov and from the National Integrated Drought Information System, drought conditions in Oklahoma and northern Texas began in August of 2025 and have persisted for nearly a year. The persistence of the drought through the 2025-26 winter, which was a neutral ENSO winter, allowed soil moisture deficits to accumulate and prevented the normal recharge of shallow aquifers and surface reservoirs. By the spring of 2026, the impact on agriculture was direct and measurable. DroughtGov's update on the Southern Plains region described this year's winter wheat yield as coming up very short, creating $1 billion deficit in production. That is the inland baseline that El Nino is now landing on top of. Now, El Nino does not fix drought uniformly. This is the part that gets lost in casual conversation. The conventional wisdom is that El Nino brings rain. That is true for some regions. It is not true for others. The southern tier of the country, where El Nino directs the storm track, can receive significant relief from drought during a major El Nino winter. California, the desert Southwest, the Gulf Coast states, and the southeastern United States are the regions most likely to see above normal precipitation. Those regions have a real chance of seeing drought conditions ease during the 2026-27 winter if the storm track delivers the expected precipitation. But the northern tier is the inverse story. The northern Rockies, the upper Midwest, the Ohio Valley, and the Tennessee Valley face drier conditions during major El Nino winters. The storm track that brings rain to the south is pulled away from the north. The regions already in drought, in many cases, are the regions that face the prospect of drier conditions in the months ahead. Minnesota, where severe drought is advancing right now, is in the northern tier. The upper Midwest is in the northern tier. Parts of the Ohio Valley and Tennessee Valley are in the northern tier. The drought that has already developed in those regions is unlikely to receive relief from this winter's El Nino. In some cases, it is likely to deepen. Let me give you a household scale way to hold this. Imagine a long, narrow garden with two halves, north and south, watered by a single sprinkler that can be pointed at one half or the other. The garden has been dry for a year. Both halves are suffering. Now the sprinkler is being aimed at the southern half. The southern plants will get water. They will revive. The northern plants will not get water. They will get whatever incidental moisture happens to drift over from the south, which is usually not enough to make a difference. By spring, the southern half of the garden will look green and recovered. The northern half will look browner than it did a year ago. That is the El Nino precipitation geography overlaid on the existing drought map. Some regions will see relief. Other regions will see deepening conditions. The regions most likely to receive relief are not necessarily the regions in the worst drought right now. The mid-Atlantic, where severe drought is currently expanding, sits on the boundary between the El Nino-enhanced precipitation zone and the dry zone, and the outcome for that region depends on exactly where the jet stream sets up over the winter. The northeast faces similar uncertainty. The southern plains, where the $1 billion wheat deficit has already occurred, is in the southern tier and has a better chance of receiving El Nino moisture, though the timing of that moisture in relation to the next planting cycle is what determines whether the moisture helps or hurts. The water supply implications of this geography are substantial. Regions in drought have already drawn down their reservoirs, depleted their soil moisture, and reduced their groundwater levels. The recovery from drought is slow, even when precipitation returns to normal. The recovery requires sustained above normal precipitation over multiple seasons, in many cases multiple years, to fully restore the deficits. A single El Nino winter cannot reverse a long-term drought trend. It can provide partial relief. It can also fail to provide relief if the storm track does not deliver moisture to the affected regions. The Drought.gov update for the Southern Plains specified the agricultural consequence in plain economic terms. The $1 billion deficit in winter wheat production is not an abstraction. It is a measurable reduction in supply. Winter wheat is planted in the autumn, develops through the winter, and is harvested in early summer. The crop that came up short in the summer of 2026 was planted in the autumn of 2025 into soil that was already drying out. The development of the crop through the 2025-26 winter occurred under drought conditions. The harvest in late spring of 2026 produced reduced yields across Oklahoma, northern Texas, and parts of Kansas. The deficit is now in the supply chain. That supply chain signal does not stay in the wheat fields. It moves outward into the broader food system, into livestock production, into the prices that households see at the grocery store, and into the budget decisions that ranchers and farmers are making right now in the spring and summer of 2026, in response to the conditions they have already lived through and the conditions they are now forecasting forward. The agriculture signal that emerges from this Drought-El Nino interaction is the next layer to examine. At the Torrington livestock market in Wyoming this spring, cattle sales ran at 9 times the normal seasonal volume, and that number is not a market trend. It is a signal. Ranchers across the northern Great Plains and the northern Rockies have been liquidating cattle herds at a pace that has not been seen in years. They are not selling because the market is favourable. They are selling because they cannot feed the animals they have. The pastures are not producing. The snowpack in the mountains is below normal. The reservoirs are not filling. The hay is not growing fast enough or in sufficient quantities. The cattle that took decades to build into productive breeding herds are being sold off, in many cases below cost, because the alternative is watching them starve. That is not a weather story. That is a supply chain signal that started in the Pacific Ocean. Let me walk you through how a Pacific Ocean temperature anomaly translates into a cattle auction running at 9 times normal volume in Wyoming. The chain runs through soil moisture, forage availability, snowpack, water rights, and the financial decisions that ranchers make on a season-by-season basis. The 2025-26 winter was a neutral ENSO winter, which means the storm track did not deliver enhanced precipitation to the northern tier. The northern Rockies and the upper Great Plains received normal to below normal snowpack. The spring melt was reduced. The reservoirs in the region, which depend on snowmelt for their refill, did not refill to their target levels. The soil moisture going into the 2026 growing season was depleted. The pastures that ranchers depend on for spring and summer grazing did not green up at the normal rate. By late spring, ranchers were running out of the forage they needed. A rancher in this position has limited options. The animals can be moved to other pastures, but in a regional drought, other pastures are not available. The animals can be fed hay, but hay costs money and the price of hay rises sharply when drought stresses production across a wide region. The animals can be sold. Selling means liquidating an asset that took years to build. It also means accepting whatever price the market offers, which is typically depressed when many ranchers are selling at the same time. The Torrington auction at 9 times normal volume is the visible end of that decision being made across thousands of operations simultaneously. The same dynamics are running in the winter wheat belt. The Drought.gov update for the Southern Plains specified the consequence. This year's winter wheat yield came up very short, creating a $1 billion deficit in production. Winter wheat is one of the bedrock crops of American agriculture. Oklahoma is the second largest winter wheat producer in the country. Northern Texas is a major producer. Kansas, immediately to the north, is the largest. The wheat that was harvested in late spring of 2026 was the crop that had been growing through the worst of the drought. The deficit, when multiplied across the Southern Plains region, exceeded $1 billion in lost production value. That deficit is in the supply chain right now. The grain that did not get produced is grain that is not available to be sold, milled, exported, or used for feed. The flour mills that depend on winter wheat are looking at reduced supply. The export contracts that depend on American wheat are being filled from reduced inventory. The feed mills that use wheat as a livestock feed input are facing higher input costs. The downstream effects, while not yet fully visible in retail prices, are in the system. Now El Nino enters this picture in a specific way. The conventional expectation is that El Nino will deliver above normal moisture to the Southern Plains in the 2026-27 winter, which could benefit the next crop of winter wheat planted in the autumn of 2026. That is a plausible scenario. It is also dependent on the storm track setting up in a way that delivers moisture to the wheat-growing regions specifically, rather than dumping it on the Gulf Coast or pulling it across the southeast. The timing matters too. Winter wheat needs moisture at specific developmental stages Too much moisture too early can damage the seedlings. Too much moisture at harvest can damage the grain. The El Niño storm track delivers persistent precipitation, but the persistence can be either beneficial or harmful depending on when it lands relative to the crop's needs. For corn and soybean producers in the central Midwest, the picture is more variable. The northern Corn Belt, including Iowa, Illinois, and parts of Indiana, sits on the boundary between the El Niño enhanced precipitation zone to the south and the reduced precipitation zone to the north. The outcome for the 2026-27 winter and the 2027 growing season depends on exactly where the jet stream settles over the winter and where the storm track delivers its moisture. The northern reaches of the Corn Belt may run drier, the southern reaches may run wetter. The transitional zone in between can experience either signature depending on small shifts in the upper level flow. Spring wheat producers in North Dakota, Montana, and parts of South Dakota face the higher risk scenario. Spring wheat is planted after the snow melts, develops through the early summer, and is harvested in late summer. The crop depends on snowmelt, on spring soil moisture, and on early summer rainfall. The El Niño storm track is not expected to deliver moisture to those regions. The 2026-27 winter is forecast to run warmer and drier than normal across the spring wheat belt, which means reduced snowpack, reduced soil moisture recharge, and a difficult planting environment in the spring of 2027. The cattle industry across the West faces a similar pattern. The southern cattle operations in Texas, New Mexico, and parts of Arizona may receive improved forage conditions if the El Niño precipitation lands on schedule. The northern cattle operations in Wyoming, Montana, Idaho, and the Dakotas face the prospect of another dry winter, with reduced snowpack and reduced summer forage. The herds being liquidated at Torrington this spring are not isolated. They are part of a broader regional contraction that has been building through multiple dry seasons. The chain that connects the Pacific to the grocery store runs like this. The food you will buy at a grocery store in January 2027 is the food that is being grown, raised, and harvested in the planning decisions that farmers and ranchers are making right now. A rancher who sells off half a herd this spring is making a decision that will reduce beef supply 2 and 3 years from now. The breeding cows that were sold do not produce calves next year. The calves that would have been born do not become market-ready beef in 2027 or 2028. The supply contraction propagates forward in time, with a lag that the consumer does not see until the retail price reflects it. That number, plus 0.7 degrees Celsius in the Nino 3.4 zone, is not an ocean statistic. It is the reason cattle ranchers in Wyoming are liquidating herds they built over decades. It is the reason winter wheat in the southern plains came up $1 billion short. It is the reason the food you will buy at a grocery store in January 2027 will cost more than the food you bought in January 2026. The Pacific Ocean is not a remote system. It is already here. The same logic applies to grain prices. Wheat futures respond to forecasts as well as to actual production. $1 billion deficit in the southern plains, combined with uncertainty about the 2027 planting environment, raises the floor under wheat prices. Corn and soybean prices, which respond to the broader Corn Belt outlook, are also being repriced as traders assess the El Niño implications. The retail prices for bread, for breakfast cereal, for chicken and beef and pork, all of which depend on grain inputs, are downstream of these supply decisions. The agriculture signal is one of the clearest translations of the Pacific Ocean temperature anomaly into consequences that older Americans will feel directly in their grocery budgets. It is also one of the slowest signals to fully resolve, because the agricultural cycle operates on seasons and years, not on days and weeks. The decisions being made in the spring and summer of 2026 will shape supply conditions into 2027, 2028, and beyond. Whether those decisions need to be revised, accelerated, or amplified depends on what NOAA confirms in its next official update, which is now less than a month away. Let me tell you exactly what is going to happen on July 9, 2026, at the offices of NOAA's Climate Prediction Center in College Park, Maryland, and why the number that comes out of that building on that day matters to every American watching this. July 9 is the date of the next monthly ENSO diagnostics discussion. The diagnostics discussion is the formal review process the agency runs each month, in which its scientists assess the state of the Pacific Ocean and atmosphere, evaluate the latest model outputs, and issue an updated classification and forecast. It is not a press conference. It is a technical document accompanied by a forecast summary. The number that the July 9 update will produce is the updated Nino 3.4 reading and the updated probability distribution for the 2026-27 winter event. The reading that matters is whether the Nino 3.4 index has crossed plus 1.0 degrees Celsius into moderate El Niño territory. The June 11 reading was plus 0.7, which is in weak territory by the standard classification. The threshold for moderate is plus 1.0. The threshold for strong is plus 1.5. The threshold for very strong is plus 2.0. If the July 9 update shows the Nino 3.4 reading at plus 1.0 or higher, the event will have crossed into moderate classification in a single monthly cycle, which would confirm that the loading is accelerating at the pace the international model ensembles have projected. The other dimension the July 9 update will reveal is whether the summer coupling between the ocean and the atmosphere has intensified. Summer is the critical window for major El Niño events. The strongest events in the historical record are characterized by significant ocean-atmosphere coupling during June, July and August, which is when the Bjerknes Feedback either gains the momentum it needs to reach very strong intensity by winter or fails to gain that momentum, and the event peaks at moderate. The July 9 update will indicate, through its description of the wind anomalies and the ocean heat content, whether the coupling is intensifying. The July 9 reading will not arrive in a vacuum. The models have already spoken. The basin has already loaded. But three things that number will not resolve are worth stating plainly, because they are the difference between a forecast and a certainty. The 63% probability is not a guarantee. The 98% model agreement is not a certainty. The structural signals in the basin point toward a major event, but operational forecasting cannot eliminate uncertainty entirely. There are three specific unknowns that the data cannot yet determine. The first is whether the Bjerknes feedback will sustain through the summer at the rate the June data suggests. The loop has begun. The loop is active, but the loop can lose momentum if the trade winds reorganize, if the Western Pacific warm pool depletes faster than expected, or if other oceanic processes intervene. The summer months are the test of sustainability. The second unknown is whether the storm track shift will produce the southern tier storm pattern that the historical El Niño record predicts, or a different track altogether. Upper-level circulation does not answer to a single driver. The Arctic, the North Atlantic, and the configuration of pressure systems across the continent all pull on the storm track simultaneously, and in any given winter, those additional forcings can amplify or partially offset what the Pacific is directing. The exact placement of the storm track in the 2026-27 winter cannot be forecast with the precision that probability figures might suggest. The third unknown is the compounding factor of a warming climate baseline. The tropical oceans today are warmer in their baseline state than they were in 1997 or 1982. The same Nino 3.4 anomaly produces different downstream effects against a warmer baseline. The 2026 event may behave differently than 1997 even if both reach the same official classification. These unknowns are why July 9 matters. Not because the outcome is unknown. The outcome is forecast with high confidence by every major international model. The reason July 9 matters is because the confirmation of trajectory is what converts probability into prediction. A 98% forecast that holds through the next monthly cycle and that adds new confirming observations from the summer ocean-atmosphere coupling is a forecast that operational planners treat as actionable. A 98% forecast that wobbles or weakens in the next monthly cycle is a forecast that planners revise. The 63% figure that the headlines cited is not a bet. It is a documented probability from the same agency that accurately forecast the 1997 event months in advance. The agency's track record on ENSO forecasting at this lead time is strong. The probability is not a guess. It is the integrated output of the same model and observation system that has called major El Niño events correctly before. The viewer who treats the 63% as a coin flip is misreading it. The 63% reflects the structural state of the basin and the convergence of international models. It is the highest confidence forecast the agency has issued at this lead time in this kind of configuration. What that probability becomes, what the July 9 reading confirms or revises, what the trajectory looks like as the basin moves through the summer and into the autumn, is the question that the next several months will answer. There is a number inside NOAA's June 11 report that the headlines never read aloud, and now you know exactly what it is and exactly what it means. Plus 2.1 degrees Celsius. The Nino 1+2 zone. The Eastern Pacific, the monitoring region closest to the coast of Peru. The leading edge of the basin. The threshold NOAA has set as the ceiling of the super event category, recorded not in November, not in December, but in June. That number does not mean a super El Niño is confirmed. The official classification will not be made until the Central Pacific catches up to where the Eastern Pacific already is, and that confirmation, if it comes, will come in the autumn and winter monthly diagnostics discussions. What the number does mean is that the leading edge of the Pacific's warmth has already arrived at peak event intensity. The Bjerknes Feedback that Jacob Bjerknes named in 1966 is confirmed as active and self-sustaining in NOAA's own June 11 language. The 13 international model ensembles are in agreement at 98% that the event will reach at least the strong category. The July 9 update will either accelerate or hold that reading, and either way, the trajectory of the next 6 months of American weather will be clearer after that date than it is today. The frame is yours now. The Nino 1+2 reading. The Bjerknes Feedback loop. The 1997 parallel with its documented 189 deaths and $4 billion in direct losses. The jet stream mechanism, the coastal flooding double whammy. The drought map overlaid with the El Niño precipitation geography. The Torrington cattle auction at 9 times normal volume. The $1 billion winter wheat deficit. The July 9 confirmation date. These are the elements. They are connected by a single physical mechanism that the agency has documented and that the international model community has corroborated. The viewer holds something now that the morning news did not deliver. The frame is not a forecast of doom. It is a frame of preparation. The southern tier of the country is likely to receive enhanced precipitation through the winter. The northern tier is likely to run drier and warmer. The coastlines, both Pacific and Atlantic, are likely to experience more frequent and deeper high tide flooding. The drought regions in the northern tier are likely to deepen, and the regions in the southern tier may receive partial relief. The food supply is already being repriced through the decisions farmers and ranchers are making in real time. The energy demand is being recalibrated. The water managers are revising their plans. What no one in the household watching this can do is undo the loading that has already occurred in the basin. The Pacific Ocean has shifted. The leading edge has crossed the super event threshold. The feedback is running. The probability has consolidated. What the viewer can do is hold the frame, watch the July 9 reading with the context that the agency does not provide in plain English, and understand that the weather of the next 6 months is not arbitrary. It is the working out of a process that began in the equatorial Pacific months ago, that was declared on June 11, and that has a documented trajectory the public record has now fully described. That number inside the June 11 report, the one the headlines never read aloud, was already past the threshold before summer began, and now you know exactly what it means. The Eastern Pacific is already there, the feedback loop is already running, and the question that July 9 will answer is not whether this is a major El Niño. The question it will answer is how close to 1997 the next 6 months of American weather intend to get.